notice, and this is the typical copyright. We continue with mathematics syllabus for CSEC 2018 to 2027. Schedule of videos. Section 1, number theory and computation. All 33 of those videos have been published on YouTube already. Section 2, consumer arithmetic. All 12 of those videos have been published in their entirety on YouTube. Section 3, sets. All 6 of those videos have already been published on YouTube in their entirety. So please make use of those 51 videos from sections 1, 2, and 3. Now we are at section 4, measurement. This is the 9th of 16 videos, and I am somewhat behind schedule. Of course, that will be followed by statistics, January 2025. Then by February 2025, end of February, algebra. March 2025, relations, functions, and graphs. April 2025, geometry and trigonometry. And finally, by May 2025, vectors and matrices. Please note this disclaimer down here that this schedule is just a projection which may or may not be fulfilled. It is not a contract with anyone. From section 1, I have divided that into 33 videos, and they are all available in their entirety on YouTube, especially since this section, which is section 1, forms the foundation on which the rest of the syllabus is based. These 33 videos here, make sure you look at them and know them very well. Another reminder, you need to know the times tables from 2 to 12. If you don't already know them, then you will have to learn them, especially since calculators are not allowed in paper 1. Just a reminder that these 12 videos from section 2 are published in their entirety on YouTube, and then these 6 videos from section 3 are all published on YouTube in their entirety. We are now at section 4, measurement. Up to this point here, the first video and the 4th video in this section have been published in their entirety. The 2nd video, 3rd, 5th, 7th, and 8th are only published partially. We are now here, objective 6 part B, which deals with calculate the area of polygons, and this is video 9 in section 4. And this video will be published in its entirety once I'm finished with it. So 4.6a and 4.8 calculate areas of circles and of triangles. That's what we did in the last video. So before we go on, recall that I said in the introductory video that you will need a good math textbook or a set of 2, especially to get more practice questions. CSEC recommends these books here. And from that list, the one I would recommend is this very good 2-volume set of math textbooks that is quite adequate for the current CSEC math exam. Volume 1, Mathematics, a Complete Course with CSEC Questions by Raymond Tulsi. And this is Volume 2. Disclaimer, I get no financial or other benefits from the sale of these books. Also, very recently, late 2024, I think, a website with AI interactivity has been made available free of cost that deals with past CSEC math questions only. You can navigate by topics or year, where all questions for the past several years have been worked out for you. If you have a question that you need explained, you can ask AI assistant either by text or voice, and most likely that will be explained to you. So this is the URL for RSC student. And the home page for that site is shown on the next slide. So that's a URL. I will include that URL in the description of this video, so it will not be very difficult for you to click on it and get to that site. This is the home page where you have to register or sign in. So this is a print screen of the syllabus. We have completed all 4 of those objectives on this page. And from this page, we have completed objective 5. And in the last video, as I pointed out, we have completed this part of that objective 6, as well as objective 8. So we are now here, calculate the area of polygons. So after we finish that, we will have 2 more objectives on this page, objective 9 and objective 7. And we will deal with those 2 objectives in one video. And then in the next page, 6 more objectives, which would give us a total of 15 objectives in this section on measurement. So just a reminder of what polygons are. If we were to put all polygons in this box here, we can start with triangles in that ellipse, and then quadrilaterals in this one over here, and then regular polygons with 5 or more sides here, and then of course we have irregular polygons. For triangles, there are isosceles triangles, and within isosceles triangles there are equilateral triangles, and then also still in triangles there are scalene triangles. For quadrilateral, parallelogram, and then kites, trapezium, these are all quadrilaterals. Subset of parallelogram would be rectangles, and a subset of rectangle would be square. But everything that you see in this ellipse here are quadrilaterals. Okay, there is rhombus as well. Now, we already learned how to find the area of triangles using 3 different formulae in the last video. This first formula here, area of triangle is equal to half base times perpendicular height. Then this next one here, if you are given 2 sides, A and B, and the angle between, the area is half AB sine C. And then we also learned this one, given 3 sides A, B, and C, we can use this formula here. That was done in the last video. So now we will deal with quadrilaterals firstly, and then we will look at other polygons. A quadrilateral is any enclosed shape that is made up of 4 straight line sides. So here you have a square, it is a quadrilateral. You have a rhombus, it is a quadrilateral. Here you have a rectangle, it is a quadrilateral. A parallelogram, another quadrilateral. A trapezium, another quadrilateral. An isosceles trapezium, which is a special kind of trapezium, it is also a quadrilateral. And we have a kite over here. So We will learn to find the area of these, though of course some of them you already know from primary school, like the area of a rectangle. All of these use basically the same formula, the base times the perpendicular height. So for the rectangle, we call the base and perpendicular height the length and breadth, respectively. So let's consider this rectangle here. Area is equal to length times breadth. So calculate the area of the rectangle shown above if its length is 12 meters. That is, this here is 12 meters, which is the same as that down there. And its breadth or width is 5.0 meters. That's this over here, which is the same as that. So area of rectangle is equal to length times breadth. You multiply the two things and you get 60 square meters. We need two significant figures. As it stands here, this could be misinterpreted for one significant figure. And so if you put a dot here, it specifically means two significant figures, or better still, you could say 60 plus or minus 0.5. This 0.5 says you are rounding off here, therefore two significant figures. CXC would prefer, actually CXC requires this format. For a square, the length and breadth are the same. So it's a special type of rectangle, but the length and breadth are the same. So we multiply the length by the breadth, which is the side squared, for a square. So calculate the area of the square shown above if its sides are 6.0 meter. 6.0 meter, all four sides. All you need to do is multiply the length by the breadth, which in this case is the side square, and we get 36 square meters, which has the correct number of significant figures. However, you can better state it as 36 plus or minus 0.5 square meters, but this is not strictly required. Now we come to the parallelogram. Now keep in mind that a rectangle is a special type of parallelogram, and a square is a special type of rectangle. So for all parallelogram, you multiply the base by the perpendicular height. Now calculate the area of the parallelogram shown above if the base is 11 meters and the perpendicular height is 5.0 meters. So this is the base here, which over here we would call the length. And the perpendicular height is going up here, perpendicular from the base, and that is 5.0 meters. Now the area of any parallelogram is the base times the perpendicular height. And so we substitute the numbers and we get 55 square meters. That has the correct number of significant figures. But if you want to be a little more precise, you can say 55 plus or minus 0.5, as this is the uncertain digit, square meters. Now the rhombus, which is this shape here, it looks like a shortened version of the parallelogram. The length is called the base, and the breadth or width is called the perpendicular height. So it's base times perpendicular height, which is this side here, times the perpendicular height. If this is 6 meters, and the perpendicular height here is 5.0 meters, as I said, in all these four shapes is the same formula. The base times the perpendicular height, not the slanting height, not the slanting height. So base times perpendicular height. For the rectangle, we will call that length times breadth. And so 6 times 5.0, and we get 30. Now this has the correct number of significant figures, which is 1. But to make sure that it is understood that it is 1, we add plus or minus 5 square meters, which means that the uncertain digit is where this tree is, which is a tens position, just to be clear. So let's revisit the area of a parallelogram or rhombus. If we overlay this parallelogram on the right here with a rectangle starting here and there along the base, you can cut out this part that is here and paste it in over here. So in essence, you have a rectangle that is 11 by 5. Essentially, we are finding the area of a rectangle with those dimensions. Same thing goes for the rhombus. If you use this base here and draw a rectangle above it, which is this rectangle here, you can remove that part from there and put it in over here. So really, we have a rectangle that is 6 by 5. If you find this video useful and interesting, please like and share. Like and share. You may also consider subscribing to this channel. So a quadrilateral is any enclosed shape that is made up of 4 straight line sides, as you see here. And we use the same basic formula to find its area. Base times perpendicular height. Of course, in the rectangle, the base is the length, and the perpendicular height is the width. And in the square, base and height, they are the same. We now turn our attention to the trapezium first, and then the kite. Now, this shape here is a trapezium, and so is this one, but this is a special type of trapezium. And that one over there is a kite. Now, a trapezium is a specific type of quadrilateral that has only one pair of parallel sides. This one here is parallel to that. Unlike the other quadrilaterals that we were looking at before, this has only one pair of parallel sides. Trapezium. In order to find its area, we need to know both the parallel sides and the perpendicular distance between them. This is from your formula sheet, where it says area of trapezium is half of A plus B multiplied by H. A and B are the parallel sides, and H is the perpendicular distance between those parallel sides. So half of A plus B times perpendicular height. Now calculate the area of the trapezium shown above if its parallel sides are 9.0 meters and 11 meters long, and the perpendicular distance between them is 5.0 meters. So if this side here is 9.0 meters, and this side down here is 11 meters, and the perpendicular distance between them is 5.0 meters, we have enough data to find the area. So we substitute the numbers we are given. We know A is 9, B is 11, and perpendicular H is 5. Substitute that, and we get 50 square meters. Now that looks like one significant figure. It is better to write 50 with a point next to it, or even better still, 50 plus or minus 0.5, meaning that this here is our uncertain digit, and therefore 2 significant figures. Now the isosceles trapezium, the 2 angles on each of the parallel sides are equal to each other. So this angle down here is equal to that one, as well as this one up here is equal to that one. Think of an isosceles triangle that is cut off at the top here, like that. And so you get an isosceles trapezium. Now, this may be useful when constructing the isosceles trapezium, but it is not very helpful if we have to calculate its area. We still need the two parallel sides and the distance separating them. So isosceles trapezium, if this side here is 4.0 meters and this side here is 8.0 meters, and the perpendicular distance between them is 6.0 meters, we use the same formula we were using for the regular trapezium, which is you add the parallel sides, find half of that, and then multiply by the perpendicular distance between them, and we get 36 square meters in this case. This has the correct number of significant figures, 2 significant figures. If we want to be more precise, we could say 36 plus or minus 0.5 square meters, making sure that this 6 is understood to be the uncertain digit. Now let's revisit that trapezium. We said that its area is equal to half of A plus B times the perpendicular height, the distance between them. Why does this formula work? Now think of those as the two parallel sides, 8 meters and 12 meters, 6.0 meters apart. So consider carefully what we are doing. If we add those parallel sides and multiply by a half, which is dividing by 2, and then multiply by the distance separating them, we get 60 with a point, 2 significant figure, we get 60 square meters. Now what is half of A plus B? If you add A plus B and then you find half of that, you get 10. Consider this trapezium again up here. We now get a rectangle whose length is the average of the lengths of the parallel sides. So consider this rectangle now. It is 10 meters long and 6 meters wide. So what really happened? We can cut off, think of it as cutting off this triangle here and putting it up here. So in effect, we have a rectangle. We are really finding the area of a rectangle. Now we split the difference equally. That is to say, this side is 12, that side is 8, the difference is 4. We divide that 4 by 2, we get 2. So what we do, we decrease this side by 2, and we increase that side by 2. And so we get a rectangle that is now 10 meters long. Continuing with trapezium. In physics, a student may be asked to construct a speed-time graph and then use the graph to find the distance traveled by the car in, say, 45 seconds. Construction of the graph is not a problem. This is a graph. Now to find the distance, he or she needs to find the area under the graph for each section and then add them up. So in the first case, from here to there, the shape formed is a triangle, as in this case here. If you find the area of A, that's the distance the car traveled during that time. And then part B, you have a rectangle here. Find the area of that rectangle. That is the distance the car traveled during this time from here to there. And then you come to here, C. Note carefully that shape. It is a trapezium. Just in case students forget how to find the area of a trapezium, you can always divide that into a triangle up here and a rectangle down here. Find those two, add them, and you will get the area of the trapezium. So let's continue. We are going to 45 seconds. This here now is a rectangle, D. The area of that shape is fairly easy to find. And then you add up all those areas and you would get the distance traveled during the first 4 to 5 seconds of the journey of that car. So let's come back to this shape at C. As I said, A is a triangle. Its area is very easy to find. B and D are rectangles. Those areas are very easy to find. But you come to C. If only the student can see a trapezium at C with parallel sides being 10 meters per second, that is this side here, and 20 meters per second, that is this side over here. Those are the lengths of the parallel sides, and the perpendicular distance between them is 10 seconds. That's from 20 to 30. Then finding the area under that graph is very easy. Sum of parallel sides, divide by 2, and then you multiply that by 10. When you multiply here, you get 150 meters. Now, I know I said we are finding the area under the graph, and we do use formulae for area. However, our answer ends up in distance, which is meters. So when we multiply meters per second by second, that second cancels out that per second, and we are left with meters. And so even though I say you find the area under the graph, which is what you are doing, the units for that is meter, which is length. Just be aware of that. It does not matter what the trapezium looks like. The same principle applies in all cases. So we can find the area of all of these quadrilaterals. We now turn our attention to the kite. Well, first of all, this is a math class, so we are not talking about a small hawk. That is a kite. Neither are we dealing with wind-powered levitation toys like these, though of course some of these do look like the shape we are going to look at, minus the frills. So the shape is this, over here. It's a kite. A kite is a quadrilateral with reflection or symmetry along its longer diagonal. So if this is the longer diagonal here, notice the half on the left over on this side is reflected on that side there. You can also think of it as a quadrilateral whose 4 sides can be grouped into 2 pairs of adjacent equal length sides. So this side here is adjacent to that side and equal, and this side here is adjacent to that side there and equal. So this is a kite, and this is what we will be learning about right now. So the area of a kite is half the product of the lengths of its 2 diagonals. Now the formula for the area of a kite is given as area is equal to half times d1 times d2, where d1 and d2 are the long and short diagonals of the kite. So let us say this is the kite. This blue here is the longer diagonal, and this red one here is the shorter diagonal. This short one here is 4 meters, and this long one here is 8 meters. So the formula we have is half of d1 multiplied by d2, which are the 2 diagonals. We substitute the numbers and we get 16 square meters. This has the correct number of significant figures: 2 here, 2 there, and 2 here. So how and why does this formula work? Now you don't have to know this. All you need to know is to use that formula. So think about it this way. if we construct a rectangle around the kite, using the lengths of the diagonals as its sides, the area of the rectangle is 8 times 4, which is 32 square meters. So if we do that, the length is 8 meters and the width is 4 meters. So the area of the rectangle is 32 square meters. But we found the area of the kite as half of 32, which is 16. So look carefully what is happening here. Notice the diagonals of the kite and the sides of the rectangle, that they form 4 smaller rectangles, each of which is only half of the kite. So look at this first one here. Look at this first rectangle here. Notice that this diagonal here divides that rectangle. So we are only counting half of that rectangle in the area. And the same thing goes for this rectangle here. We are only counting half of it. And so on for these other 2 rectangles here, that one and this one. In each case, we are only counting half of the rectangle as part of the area of the kite. Hence, we find the area of a rectangle with these measurements and take half of that. Now, this reminds you of the area of a triangle, half of base times height. So this should not be very difficult to learn. It's not as difficult as you may have first thought. Calculate the area of polygons. Now, we will turn our attention to these other regular polygons: pentagon, hexagon, heptagon, and so on. There is a principle that we will learn, and all of them would become very easy. The syllabus does not give any formula to find these areas. So the area for any polygon is this: number of sides times length of one side times the apothem divide by 2. And then it goes on to say how to find the apothem, which is length of one side divided by 2 times tan 180 over number of sides. Sounds complicated. I will show you how to use that, but you don't have to remember that formula. We can reason it out based on formulae that would be given on the formula sheet. So let us try to understand this formula by considering 4 examples. Example 1, pentagon. So this is a regular pentagon. It has 5 sides that are all equal. First, we will draw lines from the center to each of the angle, and we will therefore get 5 identical isosceles triangles. So we draw a line from the center to there and from there to there. We now have an isosceles triangle here, and we do that. That's 2, 3, 4, and 5 isosceles triangles. We will do the same thing with hexagon and heptagon and whatever other regular polygon we are looking at. We will determine how many triangles we have. Then the next thing is we will find the area of one of these triangles and then multiply by 5 in this case, because it's a pentagon. If it were a hexagon, we will multiply by 6. So this side here is 8 centimeters, and so are all the other 4 sides. We will calculate the angle near the center, the angle here. And to do that, we will divide 360, that's a complete circle, by 5 in this case, and we get 72 degrees here. So that angle is 72 degrees. Next, we will calculate the base angles. That is to say, this one here and that one there. Now recall that this is an isosceles triangle, which means that these 2 angles at the base here are equal to each other. So what we will do, from 180, Since we know that the sum of the three angles in a triangle is 180, we will subtract 72, that's that one there, and we will get the sum of the other two. We divide that sum by 2 and we get 54. So each one of these will be 54. You could add 54, 54, and 72, and you will get 180 degrees, the sum of the angles in a triangle. Next step, we will draw a line from the center to the midpoint of the base. We'll draw a line from here and come down here, the midpoint, like that. And that line will actually be perpendicular to this base. So we now have a perpendicular line here, perpendicular bisector really, which gives us two other points. If it's a perpendicular bisector, then this 8 is now divided into two equal parts, so half of it will be 4 centimeters. So look carefully what we have here. We now have a right triangle here. We know one of its angles, besides the fact that there's a right angle here, and we know this side. We will call this side H. Now we will use the trigonometric ratio tan to find this height. Now remember, once we find that height, we now have this triangle here. We know its base and we know its perpendicular height. We can use the formula area of triangle is equal to half base times perpendicular height. Find the area of this one triangle and multiply that by 5 because there are 5 such triangles. Okay, so the trigonometric ratio that we will use is tan. Now the tangent of any angle in a right triangle is the ratio of the opposite to the adjacent. So that tan 45 degrees will be h over 4. H over 4. We rearrange that and we get h is equal to 4 times tan 54. We enter that in our calculator and we get 5.5 centimeters. So now we know this perpendicular height is 5.5 centimeters. We know the base is 8 centimeters. We can use that half base times perpendicular height and we can get the area of one triangle as 22 centimeters. Okay, we are almost finished. There are 5 such triangles in this pentagon. We multiply the 22 by 5 and we get 110 square centimeters. Now, in this case, you don't have to memorize any formulae. The formula for tan is given on the formula sheet. You have to know how to use it. Unlike this formula up here. Now, at first, it seems very easy. Number of sides times length of one side times the apothem. Think about it, that apothem is actually the perpendicular height of this triangle at any one side. Now, we have reasoned out how to find the apothem. You can, of course, use this formula here to find the apothem. And we will look at that right now. If we try to use this formula up here, let's first of all calculate the apothem and then substitute that in this formula here. We know the length of one side. We know how many sides the polygon has. So the apothem is L, which is 8 centimeters, times 2 times tan 180 divided by 5. Of course, if it were a hexagon, this 5 would be 6, and so on. Then we work that out and we get 5.5. That's the apothem. That's the height of this triangle. And this is the base. So as I said, once you find this, we take that 5.5, substitute it in here, and notice what we are doing. We're multiplying 5, that's n, by the length of one side, which is 8, by the apothem, which is this. So if we do that, we get 110 square centimeters, which is the same answer we had down here. So if you want to learn that formula, fine. If not, you can reason it out to find the apotem, which is the height from here to there, perpendicular height. We can easily find the area of one of the triangles once we know the perpendicular height, because we are given the length of the sides, and then multiply by how many of these triangles we have here. So that's the reasoning behind it. Let's look at the same thing for a hexagon. First of all, we will reason it out, and then we will go back and use this formula up here. So this is a hexagon. It has 6 sides. From the center, you could draw lines going to the angles outwards, or you just draw lines going across, join the opposite angles. And this is what we have. We have 6 triangles. Again, we will find the area of one of the triangles, preferably this one here, easier to look at. And then once we get the area of that, we will multiply it by 6 to get the total area. But first of all, to get the area of this triangle, while we know the side is given, we want to find this perpendicular height. And then we can use that to find the apotem, which is the height of that triangle. So 8 centimeters. Calculate the angle near the center, this angle here. Well, we know the whole circle is 360. We now have 6 angles, so we will divide by 6 and we will get this one angle here as 60. We will calculate the base angle the same way we did for the pentagon. Subtract 60 from 180. That's the sum of the 3 angles in a triangle. And that will give us the sum of the other 2 angles. We divide by 2 and we get these individual angles here, which now works out to be 60. In this case, with the hexagon, what we have here are equilateral triangles. All 3 sides are equal and all 3 angles are equal. That only works for hexagon. We will draw a line from the center to the midpoint of this base, like that. And 2 things here. This forms 90 degrees, and secondly, it bisects this side here. So that this part here is now 4 centimeters instead of the whole base, which was 8 centimeters. We know this angle here is 60. We can use the tan trigonometric ratio to find this height here, this height here. So tan 60 is equal to the opposite over the adjacent, this opposite side here, over this adjacent side here, which would be h over 4. And you make h the subject of the formula. H is equal to 4 times tan 60, which gives us 6.93 centimeters. So this perpendicular going up here, the vertical height of that triangle is 6.93 centimeters. Once you get that, is the apotem. Once you get that, you can easily find the area of this triangle here, half base times perpendicular height. The base now is 8 centimeters. Remember, this is the base of the triangle, times the perpendicular height, and we get 27.72 square centimeters. That's for one triangle. You multiply by 6 triangles, and you get 166.32 square centimeters. We round that off to 170 plus or minus 5 square centimeters, since that is our uncertain digit based on 2 significant figures. All right, so now let's go now and look at that same question. Now, down here we have the working from what we did just now. Now we are going to use this formula to see if we get the same answer here. So N times L times A divided by 2, that is the formula. We have to use another formula to find A, which is this. So L is the length of the side. 2 is fine, 10 is okay. 180 is always 180. And this 6 is dependent on the number of sides in the polygon. And so we get 6.93 as the apotem. Was that what we had here when we were reasoning it out without this complex formula up here? And so now you could substitute that apotem in this formula here, n times the length of one side times the apotem, divide by 2, and you get 166.32 square centimeters, which is exactly what we have down here. It's up to you if you want to learn how to find this apotem. It's not really that hard. Or if you want to reason it out like we did down here. Heptagon. If we draw lines from the center to each angle, we will get 7 identical isosceles triangles. 7. They are isosceles because this side is equal to that side. Aim is to find the area of one of these triangles and then multiply by 7 to get the total area. Now, that makes sense? So this is 8 centimeters. We calculate the angle up here by dividing 360 by 7, and we get 51.4. That's this angle here. 51.4. If we subtract 51.4 from 180, we will get the sum of these two angles here. We then divide by 2, and we get one angle down here, which is 64.3. We draw a line from the center to the midpoint of the base, from up here to down here. Remember, this line forms a right angle here, and it also bisects this side. If it bisects that side, then this part here, this half of that side, is 4.0 centimeters. We use the tan trigonometric ratio. So tan 64.3 is equal to opposite over adjacent here, which is h over 4, because remember, it's just this half, not the whole side. H, therefore, is equal to 4 centimeter times tan 64.3, and we get 8.3 centimeters. Now, that is the apotem. It actually is the height of this triangle, 8.3. Now that we know the base and the perpendicular height, which is 8 centimeters times 8.3, half of that, we get 33.2 square centimeters for one of these triangles. We then multiply by 7 because there are 7 such triangles, and we get this answer. And we round it off to 230 plus or minus 5 square centimeters. Let's go back now and do it this way. So this is the formula we are using, but we now have to find A and substitute it in that. So let's find A. A is equal to length of one side, divide by 2 times tan 180 always, divide by the number of sides, which is 7, and you work that out and you get the apotem. The vertical height is 8.3 centimeters. So now, if you substitute that in this formula up here, where we have the number of sides, which is this that we were doing. We have the length of one side, which is that we were doing. And we have the apotem, which is this. All in one step, you get 232.4 square centimeters, which is what we had down here. It's up to you if you want to reason it out, and you will be given the formula on the formula sheet during the exam for tan. All you need to know how to use it. I haven't seen this formula here to find the apotem in any formula sheet or the syllabus. So finally, last one, octagon. This has 8 sides, and by now you are getting the pattern. Draw a line from the center to each of the angle. We will have 8 identical isosceles triangles. We will try to find the area of one of the triangles and multiply that by 8. Let's calculate, first of all, this angle up here. So the whole circle all the way around is 360. You divide that by 8 because there are 8 such triangles, and one of these will now be 45. That is 45. Now, if that one is 45, these two will be the remainder from 180. So we'll subtract that 45 from 180. Remember, the sum of the angles in a triangle is 180. If we take out that 45, then these two down here will be the remainder. We divide by 2, and we get the individual angle down here. So this angle down here is 67.5, and so is that one over there. We draw a line from the center to the midpoint of the base, like that. And by now you know that this line here, this H, is the perpendicular bisector to this side. So that this half is 4.0 centimeter, which forms this side of this right triangle here. We want to find H. We know this angle. So tan 67.5 is equal to H over 4.0. So that H is equal to 4.0 times tan 67.5, and you get 9.66 centimeters. That's the height. Now, once we find that height, it's fairly easy to find the area of this triangle here, this triangle, not the right triangle, the triangle itself. We get half base times perpendicular height. That's the base, that's the perpendicular height, or the apotem, and we get that area for one triangle. We multiply by 8 since there are 8 such triangles, and we get this answer. We are only allowed 2 significant figures, and so our answer is 310 plus or minus 5 square centimeters. That is if you reason step by step. Now we are going to look at the same working here. This time we are going to use this formula up here. Area of octagon or any other polygon is n times L times A over 2, where A is equal to L divided by 2 times tan 180 over n. The only thing here that changes is this n and this L. So let's find A, the apotem, 8 centimeters, that's the length of one side, times 2 times tan 180 divided by 8. And so we get the apotem as 9.66 centimeters, which was what we had here when we were reasoning it out. Once we get that apotem, we substitute it in that formula. We know that n is 8. We know L, the length of one side, is 8. And we know that the apotem is 9.66. We divide all of that by 2, and we get 309.12 square centimeters, which is exactly what we had down here. So as I said, your choice, whichever is easier to you. Oh, and there are other formula that you can use to find the area of a polygon. This other one is a variation of that formula that we were just looking at. Area is equal to half times the perimeter times the apotem. Again, you still have to find the apotem, and I think that is about the hardest thing here. 8 times length of one side times the apotem, divide by 2, and we got that. Now, if you work it this way, half, that half is this half. That perimeter is actually this 8 times 8.0, and the apotem is that. This is a variation of the formula we were using. Now, you still have to calculate the apotem. Look at them and choose the easiest one. So we found the area of polygons, rectangle, square, parallelogram, rhombus, trapezium, kite. So in this presentation, we first learned how to calculate the area of those polygons up there. They are all quadrilaterals. And then secondly, we learned how to calculate the area of regular polygons, pentagon, hexagon, heptagon, octagon, and so on. There is a pattern that you could follow. For any polygon, you can use this formula, which seems to be the hard way, but if you want to learn it, it's fine. And it's not given on the formula sheet by CSET. Or you could use the other one, where you could reason it out, because the only formula there that you would need is the trigonometric ratio for tan. Yes, you can reason it out step by step, and that seems easier to me and harder to forget. So we just completed this part of objective 6. Calculate the area of circles, we did that before, and triangles, and now we just look at calculate the area of polygons. And this brings us to the end of video 9, completing objective 6 in section 4.